I'll go ahead and get started here. So my name's Dennis Cavanaugh with the National Weather Service out of Little Rock. I'm happy to be here in front of all of you. Let's do this thing. So I do have my ham radio license, KF5 VHZ. It is expired, which I'm going to have to do something about here. But the reason I got my ham radio license, it might be a unique one. I don't actually own any equipment, which JM was making fun of me for. The reason why I own ham radio equipment is because as part of my love of meteorology, I wanted to go out and participate in field research projects, right? Like actually get my hands on the weather, you know what I mean? Like so you can experience it and feel it. And then when you go and look at it on a radar, it makes sense to you. And I did that in a field research project called Hailstone, where we literally went out and drove in fleets of vehicles doing crisscross patterns underneath the supercell thunderstorms, collecting hail as it was falling. We recorded the date, the time, exactly how big the hail was, where it was, every 30 seconds as we marched along with the supercell. I've been hit by thousands of pieces of hail, which may also inform my personality to some degree, right? However, that field research project, those relationships, those experiences, the pictures and the friends that I met out there on the field, that has built the foundations of this Skywarn Class that we have here in Arkansas, that I have here for you guys in Arkansas. Everything you see, it's not necessarily something I experienced directly, but it's either myself or some of my friends out in the field literally taking these pictures as they happened to show you some of the experiences of being out there where these supercells roam and have the best picture. And the only difference you're going to see in this class compared to reality is in Arkansas, we have lots of hills and trees. They tend to do this to tornadoes, right? They're still there. They're going to look the same, but you have to find a better vantage point to get a good shot of them. What I'm going to talk to you about is if you have a clear point, if you have a clear vantage point, I'm hoping to use all of the experience I've built in these field research projects with these friends to teach you what to look for if you are out there storm spotting as severe storms come back and hit us here across the state. That's kind of the goal of this class. The ham radio came into play because as we're out there doing transects through these storms, you often can't see the environment around you, right? You're getting hailed on, all you see is hail. Well, these same storms that produce large hail can also produce tornadoes. And once you get out away from big cities like Little Rock, Benton, Bryant, these things ain't so reliable. And I don't want to rely on my maybe 1 bar SOS cell phone signal to know somebody's telling me, hey, there's a huge tornado on you, you better get moving, right? Ham radio equipment works when nothing else does. If you're not a part of the ham radio community, ham radio works when nothing else will. That's why we got ham radio licenses. That's why we use the equipment when we had to rely on one another to keep each other safe. So getting your ham radio license, it's not just something for old folks, right? If everything else fails in society, that's the thing that's going to work. You're going to be looking for your nearest ham radio guy to make sure you can get a hold of somebody, to get resources, to coordinate rescue efforts, right? Ham radio is where it's at. It's fundamental to emergency communications. Hopefully you each have one of these handouts here. On the left-hand side, I didn't update this image. Your handout is updated. On the left-hand side, it's got contact information for how to get a hold of our office during severe weather. Notably, one of the things that changed from last year's class is this 1-800 number no longer is a thing. It doesn't work. So I replaced that with an email address for all of our forecasters. So that if you do see something, you've got your phone. I know it's a bit of a pain to type in an email address, but you save us as a contact. It's going to be that nws.littlerock@noaa.gov. NWS period, Little Rock, all is one word, at noaa.gov. It'll be listed where this phone number is on your handout there. That's how you can get us a report, send us a picture. You're always in contact with the forecaster at that email address. So instead of the phone number, we now have an email address for you, our storm spotters, to contact us with. We may get another phone number at some point, but all I can do is tell you what we have right now. Maybe if we're allowed to do this class next year, I'll have new information for you, but that's what we have for now. There's also an app you can download called MPing. It's a free app where you can just submit, it's anonymous, so you wouldn't get any recognition, but you could submit your anonymous report of whatever's happening in your backyard for free. It just uses your phone's GPS. But the rest of the information on this handout is, right now it's early February 2026, right? If you don't see another severe storm until you get into, May of 2026, I want you to have this information as a refresher. You're not going to remember every word I say today, right? But hopefully you'll have this handout and that'll jog your memory, remind you of a picture or a video or something that we're going to look at here. So make sure you have this with you. That is the state of Arkansas, right? And how many of you know what county you live in and can find it on a map? We issue our warnings by counties, and our coverage area in the National Weather Service is defined by counties. That's how local government organizes on a level that we can warn people on. So most of your counties are still based on or most of your severe thunderstorm and tornado warnings are still based on this county mentality. So it's worth knowing what county you're from and where to find that on a map if you want to look at weather information. For the state of Arkansas, all of the counties colored in blue on the center of your map there, those are the counties that we issue warnings for. If you go out west, east, southwest, southeast, those are different weather service offices that cover different parts of the state. This is divided up that your county is assigned to a weather service office based on radar coverage. That's it. No politics involved. Whoever's got the closest radar, you got that county assigned to you. That's it. That's the only reason we're divided the way we are. So we're the only weather service office located in the state of Arkansas, but 5 different offices cover Arkansas because of radar coverage. Does that make sense? And the various offices are listed on this map here, and you've got that to take home with you. The radar is the thing I want to talk to you about, though. This thing is so important that we've divided up the entire United States into coverage zones based on what this thing can do. So the radar, it's a remote sensing technology. So it's a way for us to look at thunderstorms without having to literally be in front of them to look at, right? If we want to do our job, we can't be with every thunderstorm, so we need some technology to tell us what's happening. The radar is that technology. Inside, a laser's not going to work on a television, but inside this ball sits a radar dish that spins around and sends out a pulse of energy. That pulse of energy is looking for a target. So you've heard of military radar before, right? Where the radar's looking for an enemy aircraft so that you can shoot it down. The weather radar is doing something very similar, but it can't see things as tiny as airplanes. It can only see really big things like showers and thunderstorms. So it's doing serving a similar purpose as military radar technology, but it does something very different. It's not as sensitive, but much more powerful in order to see storms from a long distance. This is what the radar is doing. As it spins around, it sends out a pulse of energy. That energy exists in the microwave range. If you're interested, I would not stand right in front of a radar in case you want you and all your jiggly bits to get fried. Not a great solution, right? It's microwave energy being sent out there into the world. Well, the radar is not just transmitting; it just sends out a blip of energy. It spends most of its time listening. So what the radar's job is actually to do is it sends out that pulse of microwave energy, and then it looks for that energy that gets scattered back to it. Now, only things that are dense enough to return that energy back to the radar are going to reflect energy back for the radar to interpret. So things that are dense enough to reflect energy back to the radar are going to be things falling from the sky. Notably, why I'm telling you the difference here is clouds are not dense enough to return energy back to the radar, so radar can't see clouds at all. They're just invisible. But anything falling from inside the clouds, that's what radar can see. That stuff is bouncing energy back to us for us to interpret what's going on inside the storm. But I want to point out a critical difference here. What the radar can see is essentially an X-ray of the storm. Well, if you took an X-ray of your body, could you find information that you couldn't see yourself? Yeah, it's the point of an X-ray, right? Does it give you the full picture, though? No. So a radar is an X-ray for a thunderstorm. We can see what's happening inside the thunderstorm. But what we don't know is what's happening on the outer shell of that storm. And there's really important information there that we don't have any way of getting except from you, right? From people in local communities looking at those clouds, interpreting what they see, hopefully from classes like this, and telling us what that threat is that we can't see on radar. Sometimes the clouds can speak to you before it shows up on radar. That's lead time, right? So you, as citizen scientists, if you get reports back to us at the Weather Service, that allows us to take your information, add it to the X-ray data, basically, and get a full picture for what's happening in all the storms across the state. And we can make a lot of good decisions with the X-ray data, but we need your help to fill in to get that full picture so that we can do the best job possible of getting Arkansans the information they need to seek cover before they get in trouble. Make sense? So that's just the radar working, right? The other aspect of Doppler radar that's important is that Doppler bit. So what is the Doppler bit? Well, just like a police officer's radar gun, based on information within the energy being transmitted out of the radar, we can do some mathematics and figure out how fast an object is moving directly toward or directly away from the radar. That's called the Doppler effect. So we're not doing the math ourselves, right? We have to be trained, we have to go to school to understand the math, but the radar's computer is doing the math, and what it's basically doing is for every storm out there, it's telling us how fast those raindrops are moving toward or away from the radar. This allows us to see wind speeds inside of a thunderstorm. As long as that storm is moving directly toward or away from a radar, we can sample its winds perfectly because of the Doppler effect. Now, something on radar, yes, sir, go ahead.
Is there any work they've done using LiDAR?
LiDAR. The question was, is there any work being done with LiDAR? And LiDAR is a different type of, LiDAR is laser-based. So I don't think it would work in a thunderstorm just because of that water absorbs the visible wavelength quite easily. So I'm not sure laser is going to give you intelligence, like microwave energy does. Microwave energy is good because it's super sensitive to water. I don't know that LiDAR's frequency is actually good at seeing anything in a storm. So it either if it was powerful enough, it would go right through, or it would just stop at the cloud top. Does that make sense? Yeah. At any rate, inside the radar, if we see something is moving towards us and away from us in close proximity, that tells us that the only way you can have air moving towards you and away from you right next to each other is if something's spinning inside there. So when we see air moving towards you and away from you and it's really close, that's how we detect the rotation before a tornado reaches the ground. And that's largely how we issue tornado warnings. So Doppler radar is great in that it tells us so much about what's going on inside the thunderstorm that we can't see. So when we take that information and add it to what you're telling us that you see with the storm itself visually, we can get a full picture to where we don't have to be there to tell you what's happening on the ground. But that only works when we're connected, right? We've got to be talking. And us trying to find a way to talk is the Skywarn program. That's basically how citizen scientists speak to the National Weather Service in a public safety arrangement so that we can both help each other. That's the whole goal of this program. So as I've told you, spotters, you're filling in the missing piece. Radar has lots of limitations. One is the X-ray thing, right? It doesn't show you the outer shell. The other thing that radar is not good at is it's only capable of shooting energy in a straight line. So this kind of makes sense. You're on a dark night, you've got a flashlight, you point it, and that flashlight beam goes out straight, right? You've all had experience with this, so you turn on the flashlight and the beam doesn't curve to the ground because of gravity. It just goes in a straight line. The radar's got the same problem, except our pesky Earth doesn't cooperate by being flat. So if we have any flat earthers out there, this is really going to ruin your day, but our Earth curves. So that means when the radar shoots out a straight beam of energy, the further away you get from the radar, the higher that energy gets off the ground, the further away you are, so that it points really far away from the radar. If you're like 200 miles away from the radar has no clue what's going on down low. It's only sampling the top part of that storm. So the further you are away from a radar, on average, the more important our storm spotters become, because you've got to visually fill in more of that missing information. You guys are pretty close to a radar here, and we still need your help. So imagine those counties that are a long distance away from one. You guys play a critical role. Now this is one of those thunderstorms where we talked about how I was on field research projects collecting hail, right? Well, for those of you that understand radar meteorology, you probably know what's going on here, and it's not good. I was located here in this yellow stuff looking for hail. I had no idea what was happening. And this is far southwest Oklahoma, as rural as it gets. So while this radar data was available, it's not on my phone, right? I'm looking at an old radar image from an hour ago. I'm just visually following the storm. Well, I'm tucked up in the clouds here. There's already a tornado warning issue, but there's no confirmation yet this is Norman, Oklahoma's radar. This is what a storm spotter, I'm here, there's no picture for you to look at there because it's just rain. I mean, I can't see the edge of my hood, right? But this is what the person sees out ahead of the storm. So they're looking back to the southwest. This is their position. And where the radar just shows, you see how the radar energy here, that green, how there's like a hole inside that hook? The radar shows there's nothing there. And this is what a storm spotter sees. I see nothing because I'm fully rain wrapped. What's there? Is that nothing? No, that's probably not good news, right? I mean, this is pretty clearly a tornado. You might think the edge of it is right there, which would make sense. But the weird thing about a tornado is, for one thing, radar didn't see it. It's empty. It's saying inside this hook, there's nothing. A storm spotter can clearly see that's not the case. But what's radar doing? It's shooting up here. It doesn't see this. It has no idea what's happening down there. And another thing, this is not the tornado. That's water that got sucked up in the tornado. You want to know how big the tornado is? Look for the debris. The tornado at least extends from here all the way off the image until the debris turns into rain, which I am about 100 meters from. This is an EF3 tornado absolutely demolishing a town while I'm driving along the road. I had no idea. Looking for hail, annoyed that I couldn't see the end of my hood. This is how storm spotters help, right? We need that information. Now, there was already a warning out, but how much more does that warning mean when I tell you storm spotters have seen a half-mile wide tornado headed for Tipton? That lands a lot harder than, National Weather Service has issued a tornado warning because radar says so. People don't react to radar says so. They react to voices in the community telling us there's a threat, telling us how big that threat is, and that it's headed your way. That instinct that people would, when they understand that metaphor that you're providing for them, they personalize it, and that's what saves lives. That's what makes warning so difficult, is that you have to convince people to get out of the way, not just tell them, hey, radar says this thing's coming. Yes, sir.
What part of Oklahoma was that? Southwest?
Southwest,
So
yeah.
approximately how far away would you say that image is from the radar? I guess it was Tulsa, I presume?
Norman, Oklahoma.
It was Norman, so how far away is that from
And-
the actual radar then?
Well, they have an extra radar, kind of like Arkansas has Fort Smith. And so their extra radar is at Frederick. You can see the radar kind of down here.
I mean, is that,
So that's like 2 counties away. I'm going to say that's maybe 35 miles away.
so even 35 miles away, it can't see the lower part of the storm?
No, sir.
Wow.
No.
I would've thought
It's already shooting up here about 3,000 feet.
That's a pretty
Which-
flat part of the country too.
It is, and it's just above this, just barely above it. Yeah, the only time a radar truly sees, a tornado like in the reflectivity field like this is when it's very, very close to it. And then it's so hard to know what you're looking at. Radar meteorologists get confused, and they often look for a more distant radar so that it makes sense. Because the closer you get to a tornado, the more you realize it's not a solid thing. So as you get closer to it, this doesn't get darker and bigger. It gets less filled in and more confusing. That's very difficult with being too close to a tornado. And we'll see some pictures of it. It doesn't look solid. The closer you get to it, you just see the individual wind elements flying around and don't realize you're in trouble until you're in trouble, right? So it makes them so hard. That's why you want to stay away from them and not get close if you do see one. So our warning system, this is how our warning system is basically designed, right? In order to take action, we send a warning. We just assume people understand what it means, and then we assume that they believe it and that they're going to get in their basement or whatever's best for them to avoid that bad thing. We know it's not quite that simple, right? What do you guys do with tornado warning, Saline County? What's your first action? Go outside and look, right? That's the honest answer. Nobody runs to shelter. You're gonna run outside and look. And that's the natural reaction. So this warning system breaks down if you make these assumptions. You can't do that, right? You've got to give people time to not just get the warning, not just understand it, but give them time to personalize it, to believe it's true, whatever that means to them. Look out the door, call a buddy, turn on the TV. All of that needs time for people to get to that safe space. And we want to give them that time. But we're also not Harry Potter, right? I can't make magic things happen. So we need to work within the confines of reality to try to get people to that safe space as quickly as possible. And your reports help that. You adding that human element. That radar is so impersonal, people just don't trust the raw data. Your report of exactly what you're seeing means a great deal into the response of people in harm's way. So even if you think everybody has the information you have, you guys play a large role in helping people believe that that warning is real so that they do the thing we want them to do and not die in the face of that tornado as much as we can control that. So things that we're going to talk about in this class, I'd like you to be able to visually identify and report hail, wind damage, clouds that precede a tornado itself, right? What do you need to see to verify that you have 100% for sure seen a tornado? And any time of year, we need your reports. You're a storm spotter. We're going to talk about severe weather here, but your winter weather reports matter just as much. As opposed to what you might see on television, the radar doesn't come classified. Like the radar doesn't just tell us, oh, hey, it's blue, it's snowing, it's got to be sleet because it's pink, oh, it's got to be freezing rain because it's red. Those are all algorithms making stuff up. We don't know what's happening in your neighborhood unless you tell us. So winter weather too, I know right now you understand because we're a week out from a massive sleet storm, but anytime you provide us reports, we can do a better job forecasting and giving you the information you need for the future. So please do so. We want to hear from you. I don't know if I've made that clear, but we desperately need your reports to do our job well. So who's a Skywarn spotter? Well, hopefully you guys, maybe not that close to a tornado, right? We want you to get out there, but we want you to do it safely, and we don't want you to get hurt. Your number one goal as a spotter is to keep yourself safe. Nothing else actually matters, right? If you're not safe, there's no scenario in which you risk your life to give us a report. That scenario doesn't exist. That's you being a bad spotter if you put your life at risk. Just don't do it. Give us safe reports. Those are the types that we're looking for in this class. So, any questions about storm spotting or why I'm even teaching this class? All right, let's talk real quick about how a thunderstorm works. So what makes a thunderstorm tick? Well, I'm going to take an ingredients-based approach here. You need at least 3 things just to get any thunderstorm any given day. And that's going to be the heat and humidity, something called instability, and something called lift. Now the heat and humidity. I've been here in Arkansas for 10 years. The heat and humidity, it's always hot, but we hardly ever get humid, right? So if we could just get some of that moisture and humidity here in the summer, we could get a lot of storms. No? Oh, really? Are you saying it's hot and humid in Arkansas? No. Okay, so is that box slightly easy to check for us? How many days is it hot and humid in Arkansas? How many days of those that are hot and humid do you always get a thunderstorm? Some, not all, right? So heat and humidity, we always have it, but it's not enough. So we need something else. We know the heat and humidity is necessary for storms, but we also need these other ingredients to allow a thunderstorm to actually develop. Now the instability, this is the thing we're often lacking in the summer. If we're super hot and super humid, but as you go up in the atmosphere, if it's also super hot up there, as that hot humid air rises, it's going to hit that hot desert air and sink right back down. No thunderstorm. Have you ever heard of that? That's called the cap. If you've ever heard of that terminology and you follow weather. So the cap is, to our west, there are deserts that sit up 5, 7, 8,000 feet, right? We're talking Arizona, Southern California, New Mexico, all that desert air sitting up there, thousands of feet. Well, weather systems tend to move west to east across the United States. So that hot desert air, as it gets blown to the east, it doesn't hug the ground. It just maintains its altitude. So that hot desert air, as the altitude goes down, the air doesn't. It just sits at the same level. And when that hot desert air moves over Arkansas, it prevents the hot, humid air trapped underneath from escaping into a thunderstorm. So we need the instability. The instability is actually a fancy way for saying we can't have hot air in the top of the atmosphere. We need cold air. So that's one of the parts of our job as meteorologists, is to not just track where it's hot and humid, because duh, right? It's Arkansas. The whole place is hot and humid. But where is this cold air aloft? What's going to remove that cap so that thunderstorms can develop? And that cold air aloft, it's got lots of different terms. If you've watched the TV news, you've probably heard them. Upper level storm system, shortwave trough, upper level front, the jet stream itself, right? All these are different ways of tracking cold air aloft, and that's basically how we assess instability. If we have a lot of hot, humid air down low, a lot of cold air on top of it, as that hot, humid air rises, it has a place to escape. So it's basically providing a vent to allow a thunderstorm to develop. The last thing is lift. So if you have all the fuel in place, if you have a place for the fuel to go, you've set the stage for a thunderstorm. The last thing you need is something to give everything a shove, to kick the whole process off. So that shove is going to come in the form of tracking low-level weather systems that we call fronts. A front is just going to be a change in the low-level air characteristics. So a cold front is cold replacing warm. A warm front is warm replacing cold. The whole thing is it's low-level air surging in a particular direction. As that low-level air surges and gets lifted up, if that warm, humid air gets lifted up into cold air, the whole thing takes off all by itself and we get thunderstorms all over the place. And those are the three basic ingredients, the three things that we need to come together to get a thunderstorm in Arkansas. Doesn't mean it's going to be a bad storm, just the presence of lightning from rain, right? These are the three ingredients you need. The last ingredient that you need to determine if a storm is going to be bad is something called wind shear. Now, wind shear is a change in wind speed or direction with height in the atmosphere. And that's a really complicated definition, right? In order to make this hopefully a little bit simpler, I just want you to look at this video and tell me which way are the clouds moving, from left to right or right to left. And hopefully it will demonstrate how wind shear works. So which way are they moving? Both ways, right? Depends on the level you're looking at. That's wind shear. Now notice it doesn't matter if it's hot and humid, it doesn't matter if there's instability, it doesn't matter if we have lift. That was wind shear just with average clouds on an average day. You don't need the ingredients for a thunderstorm to have wind shear. Wind shear is normal, but when you have wind shear and you add the ingredients for a thunderstorm, it takes your average thunderstorm and makes that thunderstorm super, super powerful and capable of doing a lot of bad things to a whole lot of bad people. So what we look for to determine if a storm's going to be bad or not is largely just the wind shear. If we otherwise have the ingredients for a thunderstorm and you add wind shear to it, that's how we know it's going to be bad. Wind energy is essentially hidden energy in the atmosphere that the thunderstorm can take advantage of and convert from horizontal energy into vertical energy. And this is just hopefully a good visual demonstration of what the atmosphere looks like when all the ingredients come together here on the left for a thunderstorm, but we have very little wind shear, and what it looks like when the ingredients come together on the right when we have a whole lot of wind shear. So I'm just trying to visually demonstrate the available energy in each system. The first one. Slightly different outcome, right? So on the first example, again, we're just looking at total system energy, all the ingredients for a thunderstorm, but no wind shear. Is that dangerous at all? Could be, right? It's not dangerous from the vantage point of that they were taking the video from. What about if you just put your hand around that thing? Ain't gonna tickle, is it? No, that's going to leave a mess still. So it's not that this isn't dangerous. It's just that when you get thunderstorms in this environment to experience the danger, you basically have to be right on top of them. Does that make sense? No wind shear doesn't mean the storm can't do anything bad, but you have to be like right under it to experience that bad thing. Now, in this scenario, obviously, you couldn't just stand next to it and be still okay, right? You saw the guy hightail it out of there. In this scenario, all this means is that storms are still dangerous. They can still do bad things, but they'll come to you. You don't have to go to them. So this is a much more widespread hazard, right? Something like this gets lit around you, you have to move. This one, you can assess whether you're safe or not, maybe watch it. Not so much in this case, right? When you add wind energy to the equation, everything is amped up. So that's largely what we're looking for to determine if bad storms are possible on any given day. So as meteorologists, when we're trying to make a severe thunderstorm forecast, and what I've really just shown you is what we do under the hood, right, at the National Weather Service. Like, what are we looking for? We're sitting there telling you, oh, it's a level 3 out of 5 day for bad storms. Like, what does that mean? Well, what it means is we've assessed that balance of ingredients, right? If we have all the ingredients for thunderstorms but no wind shear, we're going to tell you we might have a couple of severe storms, but they're probably not going to do a whole lot unless you're right underneath them. It's like every summer day in Arkansas, right? Every summer day, you get really big, tall storms. They're there for 45 minutes, then they're gone. When they do damage, it's usually just right around where that storm collapsed, and that's it. All the way over to when you have the most amount of heat and humidity and wind shear available for a thunderstorm, you get this special class of thunderstorms called supercell thunderstorms. What a supercell thunderstorm does and what makes it so dangerous is that wind shear that I showed you on that picture where the clouds are moving different directions, right? Nothing bad is happening. Well, what that's doing in the atmosphere that you can't see is pretend like my arm is a cross-section of the atmosphere, right? If the top part blows faster than the bottom part, it's going to start doing this. Does that make sense? Top being pushed faster than the bottom. That's it. That's not dangerous at all until a thunderstorm sucks that tube up. As that tube gets sucked up, it turns this benign into this that we all recognize and don't love, the vertical rotation that can result in a tornado. Well, that vertical rotation from the thunderstorm is birthed from wind shear. That becomes the core of that storm, which makes the updrafts much stronger, makes the downdrafts hit harder, and it allows for the generation of vertical rotation in that thunderstorm to reach the ground in what we call a tornado. That's why we're so worried about supercells. So when you have a day when those severe weather risks get really ramped up, it's because not only do we have heat and humidity and fronts, but we also have that rotation present that can be sucked up into a thunderstorm and produce a tornado on very short notice. Does that make sense? All right. After all that, you guys should be able to make your own severe storms forecast. I'm freaking tired, let me tell you. I don't really want to do it. You guys are good to go, right? Okay, maybe not. Maybe that's not really the goal of this class. So that's our job, right? That's why they pay us money to work at the National Weather Service, to look at all this stuff, make sense out of it, and then tell you what we think is most likely to happen. That's our job. And you can rely on us to do that. You go to our webpage, weather.gov/LZK, you are going to find a web page designed by meteorologists, and it looks like it. It does not look pretty in the least, right? If you have your favorite commercial web page, that's fine. Keep using it. Ours is not going to replace it in terms of aesthetic. It ain't pretty. But if you're just looking for the bare bones, is dangerous weather possible over the next 7 days? If so, what does it look like for me? That's all we deal with. We are a public safety organization. We forecast the weather, but it's only because of public safety, right? You can get a 7-day, 10-day forecast on your phone. You don't need humans to do that for you, right? But you do need humans to tell you what it means and how can it inform your decisions to help keep our communities safe. That's what we are all about at the National Weather Service. We're on Facebook and Twitter at NWS Little Rock. And you can get official forecast information from us. I would say if you're going to visit us on Facebook, we just provide like high-level updates. Like what's this big winter storm going to do? Or what's the severe weather look like for the next several days? If you're looking for like what's happening right now, where are the bad storms, you'd want to use Twitter. Facebook throttles us if we post too much, so we can only post the high-level stuff on Facebook and the more tactical stuff on Twitter. And even that is automated. It's just making sure that if you're following us, you get that tweet that says, hey, there's a warning here, there's a warning here. It might drive you nuts if that's all you do, but it's there if you want it. One of the first ways that people are exposed to the National Weather Service is we probably interrupted your favorite game or show or whatever, right? You heard the message. The National Weather Service has issued a tornado warning for Saline County until 8 p.m. Or the magic people behind that, right? So what's the purpose of these warnings? It's not for popularity. I promise it's not to irritate you from watching your favorite show or game. It's for public safety. It's the only reason we exist as an agency is to give you information to hopefully make a decision that will save your life. But the person saving your life is still you. You have to make that decision. We're just telling you where the bad thing is. You still have to get yourself to safety. So I've already told you what your role is in helping people personalize that warning. I did not tell you how you can get a warning and understand what it means. So let's tackle that here real quick. So available information, how can we get you a warning? There's lots of different ways. Inevitably nowadays, most of them come down to some form of this, right? So your cell phone is in some way, shape, or form probably going to be the first way in 2026 that you find out about a storm. If you happen to be watching live local television, they'll usually break in and let you know what's going on. You probably have a favorite weather app. You can get it on there. any of these ways are viable ways to get weather information. I just want to make sure you are using at least one, ideally more than one, because any one of these systems can and has failed in the past. And so we always want you to get a warning. The only way the Weather Service can directly get a warning into your house is if you buy one of these things. Really, really old technology, but it's still there, a weather radio. A weather radio, we consider these like smoke alarms for tornadoes. When was the last time you used your smoke alarm for entertainment in your house? You just want to get the whole house dancing, right? Press the test button, yeah. 2 a.m., let's do it, right? Nobody does that stuff because it's nonsense. The same thing with your weather radio. You're not going to listen to it for entertainment. It's boring, it's obnoxious, it's repetitive. I get it. I don't want you to buy one so that you can listen to somebody talk all night long. I want you to get one because it'll make a really loud, obnoxious noise at 3 in the morning when that tornado is headed for you and you're still asleep. It's the only thing I care about, is that you get that warning. It doesn't have to be a weather radio, but find your thing, right? Find your thing, make sure you've got at least one way, because if the tornado knocks down the weather radio tower, well, that's out. And then what? Same thing with cell phone towers, right? Have more than one way to get weather information so that you and your family are in the best position possible. The next thing is, if you get the warning, what the heck is it telling me? So we issue two different things, right? We issue severe thunderstorm and tornado watches and severe thunderstorm and tornado warnings. So which one is worse, a watch or a warning? And for the most part, we've grown up in American society. Most people know that warning is the worst thing, right? Warning means, oh my gosh, it's for real. But I've been learning Spanish and Japanese on the side, incidentally. In Spanish, these words mean the exact opposite thing. That's not so good, is it?
What does it mean in Japanese?
I haven't gotten that far yet in Japanese, so I don't know. But in different cultures ascribe different meanings to these words. So all I can tell you is that if you encounter these phrases in American English, this is the meaning they have. This is what we're trying to convey to you, that a watch means all the ingredients are there, right? But yet we don't have the final product. So the watch means that, sure, everything's there. So if we're looking at a pizza watch or a pizza warning, in the pizza watch condition, are you ready to eat it? Not quite. It's not there yet. But it could be, right? It's got potential, gosh darn it. You just got to put all those ingredients together and stick it in the oven. But that's the point. Severe thunderstorm and tornado watch means all the ingredients that I just spent all that time boring you with are there. Doesn't mean a storm has happened yet, though, right? That's just a watch. Maybe it means a watch, tornado watch means clear out the severe storm shelter. Well, I've been using that thing as a closet for 2 years. Clear it out. Make sure everybody in your house can get in there. That's a good thing to do at the watch phase. Doesn't mean panic, it means prepare. The warning. Now we got a pizza warning. You're really hungry. Can you eat? Yes, the pizza warning's in effect, right? If the thing is there, you can eat it. So severe thunderstorm and tornado warning means the thing is there, but you don't want to eat it. You want to get to shelter, right? You want to stay out of the way. But the meaning is the same. The severe thunderstorm and tornado warning means that we think, from the best of our technology, we think that that thing is there and it's headed right for you. It's time to do something about it so you don't get hurt. That's the whole purpose of the watch and warning process. And again, I know in different languages, these mean different things. All I can tell you is what it means in this country. So that's where it is. Any questions about that before I move on? Okay. So the entire team, we're responsible for issuing that warning. Where it goes from there, we are not responsible for. And that's why we're teaching this class and why we work so closely with our broadcast media partners, why we work so closely with our first responders, because we detect the threat. This is what our office looks like, right? You see tons and tons of computers. This is our direct operations floor. And then you see all these nerds sitting in front of those computers. That's what the Weather Service is, right? We're the nerds staring at the computers. Well, we don't have a whole lot of these things though. Windows. That's where we rely on you, the storm spotter, to tell us what you see. You let us know what you're seeing, and you're the windows, right? That's what your role is in this process. You're the windows for us, so we know what's actually happening out there. Once we take your information, what we see on radar, combine it, issue that warning, then the first source a lot of people still go to, even nowadays, is they turn on your local TV person, because it's a face you know and trust, right? You've seen that face in your living room for 10 years, and that's who you want to listen to, a reassuring voice when the bad stuff is coming through. I want you to still do that. That's fine. I'm not trying to take the place of your TV folks. They do a wonderful job, and when the storms are out there and you want to know what's happening right now, it's a great place to tune in as long as you have electricity. Right? And if you don't, that's why you have some of these other ways to get warning information in case the power goes out. But we combine all of these people working together. We call our integrated warning team. We're a part of it. We start the process. But you guys help get that message to the people that need it most at the exact time they need it most. And we can't do it without you, without any of you. So we always appreciate your participation because, again, as a public safety organization, we just don't want people to get hurt. That's it. So if we can plug into that system to help people avoid getting hurt, that's what we want to do, and that's why we're talking with all of you as well. It is a special day today. Groundhog Day. I don't know if any of you notice our favorite local guy here, right? Yeah. So this is Arkansas's version of Groundhog Day. Do you guys like it? It saw its shadow, so what does that mean? 6 more weeks of winter. Oh no! I did get Todd's permission before posting this, so it is AI generated content. Todd was not actually holding up a rabid raccoon. But between Mr. Jacobian and Mr. Covert, I was able to mesh their images into one, what I feel is a beautiful rendition or reenactment of Arkansas's Groundhog Day. All to point out, weather forecasting in this state is tough, isn't it? We get all types of weather. We don't just get all winter weather. We don't just get all severe weather. We get it all. Sometimes within the course of a single week, as some of you I'm sure are well aware. This video doesn't have any sound, so as you watch it, I don't want you to think you're missing out. This is just some guy that went out on his average day just trying to run an errand on the farm, right? I just want to show you what it may look like to not have weather information on any given day. I mean, again, obviously it's raining, it's windy, but guy's just going to run an errand, that's all. And maybe not the safest time to run an errand. Maybe.
Guess it's a good thing you got out of there.
Right? So this is all I want you guys to do, right? The Weather Service. I don't want you in positions like this. I can't stop the tornado from hitting you or your property. There's nothing I'll ever be able to do to influence the weather. But what I hope to do is to get you information so you don't make that same decision and accidentally drive into one, right? That's our goal in our agency, is to give you information so that you can simply make better decisions than if you didn't have the information in the first place. That's our whole goal as a weather agency. I'm going to talk to you a little bit about severe thunderstorms because I feel like I've done a lot of focusing on tornadoes. And most of you in this room, while most of you will not be hit by a tornado in the future, almost all of you will be hit by a severe storm. So let's talk about the thing that you will almost definitely encounter in your life here. Any severe storm. So in America, we have decided that a severe thunderstorm constitutes a storm that is capable of meeting these 2 criteria. provide 1 inch or larger diameter hail, which is about 2.52 centimeters, not that you're keeping track at home, or 60 mile per hour or greater winds, right? If a storm is capable of doing this or more, or worse, then we issue a severe thunderstorm warning. Can a thunderstorm still produce damage below these thresholds? Well, yeah. A 50 mile an hour wind can still blow over a tree and you wouldn't get a warning for that. This is just from talking to Americans as a whole, these are the thresholds that Americans have wanted to be warned about. So that's where our current thresholds are. Can't guarantee you they'll be there forever, but these have been in place for quite a while, so they're probably going to stick for a while. At any rate, a storm that can do these things has a very strong updraft and a very strong downdraft. The updraft supports the large hail. The downdraft brings the strong winds from the top of the storm down to the surface. The updraft and the downdraft part of these storms are the two things I want you to visually identify as storm spotters. That's what I want you to focus on. Not, oh my God, is this thing producing a tornado or not? Updraft and downdraft. That's going to be your key points here. Of course, any rotation in that storm could lead to a tornado, but if we thought the storm was going to produce a tornado, we'd issue a tornado warning, whether or not it meets these criteria. A tornado warning is just for the simple act of a tornado being produced, regardless of these two criteria. But a severe thunderstorm warning won't be issued unless one of these two criteria is met. They can both be met, that's fine, but one of them has to be for us to issue a warning. For severe thunderstorm warnings, on average, these things are not going to alert your cell phone. So most severe thunderstorm warnings, you'll have to do something else. Download an app. You don't have to pay money, but you may have to download somebody's free weather app or something if you want to get all severe thunderstorm warnings. The only time you're going to get a severe thunderstorm warning without any weather app on your phone is if in addition to the first criteria I talked about, if that thunderstorm is capable of producing hurricane force winds or stronger, so that's 80 mile an hour winds, technically 74, but regardless, 80 mile an hour winds or stronger, or baseball size hail or larger, we'll consider that a destructive severe thunderstorm that you need to take the same actions, even though there's no tornado, you need to take the same actions that you would for a tornado warning, because 80 mile an hour hurricane force winds and baseball size or larger hail are deadly on their own without needing to be a tornado first. So you're basically getting tornado warning level notification for just a severe thunderstorm, even though the word just is wildly inappropriate there because we all know hurricanes are bad, right? They're not tornadoes, but that's really strong straight line winds doing a lot of damage. Hurricane force winds, baseball hail, that's going to automatically hit your phone. All other severe thunderstorm warnings, you would need to download an app in order to get those. All tornado warnings will hit your phone no matter what level of severity. Yes, sir?
As far as wind, last few years maybe, on the nets, wind has not been reportable criteria. Is that still goes on? Like it's usually not reported, or?
Yeah. So the question was about on ham radio nets whether the wind is reportable criteria. What I would recommend in general, I mean, if you're participating in Auxcom, I'd say just follow the protocols that JM gives you all, but in a general sense, I would say report the impacts. So instead of saying, oh, I've got a 52 mile an hour wind here, I would say, hey, there's a tree down over, First and Maple. So, you know what I mean? Like, you see a tree over a road, I would report that more so than trying to guess the wind. Even meteorologists are terrible guessers of the wind. So unless you have like professional anemometer, yeah. And if you have an anemometer and can report the actual wind speed, that's fine to me. But I would listen to your actual nets, whoever the net controller is, listen to them, and then on average report impacts. But professional equipment is very welcome if you have it, for sure. Okay, so again, as we transitioned into actually showing you pictures of storms here and teaching you how to interpret them, the big thing I want you to focus on is the visual appearance of the updraft versus the downdraft clouds. If you can figure out what the difference is between the updraft and the downdraft part of the storm by sight alone, you don't need to reference anything, you're going to be better than 90% of the storm spotters out there. Yes, even those guys streaming on YouTube and stuff, you will be better than them if you can do this simple thing. Here's the updraft part of the storm, here's the downdraft by just looking at the storm. If you can do that, you're well on your way to being a great storm spotter. If you've got these two things down pat, then we start to worry about, is this thing a supercell? Is it rotating? How can I visually tell? And if you can get that down, then we worry about, is this likely to become a tornado? But you have to go through the big stuff first, right? You can't, everybody wants to jump down here. Is this a tornado? And I'm telling you, you can't do that successfully without knowing the big picture first. You're gonna have tons and tons of false alarms. So let's get you there. The updraft part of the storm. As the name implies, this is where all the air is moving from the bottom of the storm, the source of all the heat and humidity, being transferred up to the top. So the air is moving up. If you are below this part of the storm, you wouldn't really notice anything because the air is just going straight up over your head. You wouldn't feel that. It's not like you're going to be suctioned up like a kid under a vacuum cleaner, right? So, but you won't feel the air rushing up over your head, but you'll see some of the signs. What the updraft is doing though, it's not just sucking up the heat and humidity directly below the cloud, it's sucking up the heat and humidity from a good 5 miles away from that storm. It's all the heat and humidity that storm can draw in goes up and forms the big billowing clouds. That's not the air just under the storm though, it's gathered from a long ways away from it. If you're under the updraft and you don't realize it, the one thing you should note is that there's zero rain under the updraft. If you're under the updraft and you're getting wet, you're not under the updraft. There's nothing falling under the updraft. All the air is moving up. The reason why I'm telling you all of these things, if there's a tornado, it has to occur underneath the updraft part of the storm. Most of your thunderstorm is not the updraft. Your updraft, once your storm is full, big, mature, producing rainfall, the updraft only makes up 10 to 20% of the volume of that final thunderstorm. Usually on the 10% side or less when it's a big supercell. So the updraft isn't the biggest part of the storm, it's about 1/10 of it, but it's the most important one to find visually if you want to find the tornado ever. You have to find the updraft first and then work your way down to see if there's a tornado, if you can safely do so. Most of your thunderstorm is this, downdraft. So the air only goes up in like a one cylinder part of the storm, but all that heat and humidity that's transferred up, it cools, it turns into raindrops, and it falls as rain and hail. If you're getting rained or hailed on, you're in the downdraft part of that storm. The downdraft part of that storm is most of the thunderstorm. If you remember all the times in your life that you've been through a thunderstorm, you probably remember the feel of the winds, the change of the temperature, the coolness of the rain, right? These are the things you feel. If the storm is hitting you and you feel it, you're in the downdraft. That's the best way to know that you're in the downdraft part of that storm. All of the rain and hail has to fall in the downdraft. There's no tornadoes in the downdraft part of the storm itself, because tornadoes are only going to form from air that's rising up, not from air that's sinking. So if it's super windy, if the rain is super heavy, it's going to be a nasty storm, but not have a tornado exactly where you are. There are lots of bad things that can happen in the downdraft that don't come from a tornado, right? Really large hail. What about early April of last year? Like 5 days straight of flooding rains, right? The downdraft can do lots of bad things, just not a tornado. So I don't want you to discredit the downdraft because it does most of the bad stuff that you hear about, but I don't want you to be afraid of a tornado if you find yourself in one either. So here's a schematic view of how the updraft and the downdraft are typically oriented in a thunderstorm. The updraft tends to be the backside of the thunderstorm. And before the storm has enough cloud up there to produce any rain, it's all updraft. That's all there is at the beginning. But once your updraft is established and that storm is producing rain, the thing that separates the updraft from the downdraft is going to be the winds aloft. So remember when I told you about wind shear, right? Without wind shear, the thunderstorms don't last long and they don't tend to do bad things to very many people. Well, the wind shear allows these two things to be separated. If the updraft and the downdraft don't have separation, these two things come together. Well, as that warm air goes up, the rain falls right back down into it, knocks the warm air out of the way, and the whole storm dies. So the whole fact that the warm air is separated from the down air is just by those stronger winds aloft. So as your rain is produced, the strong winds carry the rain away from the updraft before it can hit the ground. This separation between updraft and downdraft, the longer it can be maintained, the stronger your storm tends to get and the more opportunity it has to hurt more people. Yes, sir?
Is the updraft the low pressure, and the downdraft is the high pressure side?
Yes, that tends to be from a surface perspective.
Is it literally moving conical like you're saying?
It is.
Okay.
Yes, sir. Yep. Yeah. Now in the middle of your updraft, you'll have a low pressure center that's going to drive the air up. So from a ground perspective, the air pressure lowers because it's air moving up. Over here, the pressure would tend to rise because it's air hitting the ground. Everything's opposite when you go to the top of the storm, but we won't get into that. But at any rate, yes, from a surface perspective, low pressure here, high pressure here. Air's moving away from it, giving you low pressure. The air's moving towards it, giving you high pressure. The longer these two can be separated, on average, the more bad things this storm can do. And if this were to hit you, like let's say that in this wall cloud there is a tornado. The way you experience this is the gust front hits you first, right? The winds shift, the temperature drops. Then you get into the rain. The rain starts off light and then it gets super heavy. Well, as you get closer to the updraft, the hail is heavier, so it falls out close to the updraft. So then your rain starts to mix with hail as you get closer and closer to the updraft. At some point, the rain goes away and you're just left with hail. And then before you get to the eventual tornado, you transition to underneath the updraft. And that sound, that transition from all this hail just beating down on the roof, all the wind making all this noise, all the rain hitting the windows, it just dead silent. And it's creepy as all get out if you've never experienced it before. But that's how it would feel, the transition from the downdraft into the updraft. If you weren't looking, that's how it would feel. And then you have that silence, maybe up to a minute before the tornado hits, if it's there. Usually there's not one, but that series of events is a big red alarm. Don't get out of your shelter, right? You experience that dead silence moment. It is not safe to get out. You wait until the other shoe drops because it's coming. So one shape or form, it's coming. But that's only would happen if the tornado was coming directly at you. I just wanted to give you that experience in case you don't go out and look at it and just feel it happening on top of you. So that's a schematic view, that's a cartoon view, but this is an image taken from a flight. So you can actually see, like I'm not making this up, right? I'm not using a cartoon to dramatize things here. You can see the updraft. That's all it is, this cylindrical corridor right here. That's the whole updraft for the whole storm. And you see below it, there's just this flat cloud, nothing falling here. Look at the whole rest of the storm. What is this stuff? It's rain, right? That's the downdraft part of the storm. And you can also see that the rain producing part of the storm, much, much bigger than the updraft. This is all there is to the updraft. This downdraft continues way off this screen to the back of the storm. All right, so we're going to come back and we're mainly going to focus on how do I look at clouds and understand what they're telling me. So that's what the whole purpose of after the break is looking at here. And what I want you to see here is this is before a storm produces rain, this is all updraft. So I'm just basically showing you a loop of how the updraft clouds, what they look like as in a time lapse as they're evolving through time. And so you can see they have these characteristic kind of fluffy white cumuliform, a cauliflower-looking appearance to them. And that's what we're really looking for when we're looking for updraft clouds. Now, I know you've all seen a cumulus cloud on a lazy summer day, right? I don't want you to, every time you see a cumulus cloud, I don't want you to think, oh my God, a tornado is coming to kill us, right? That's not the case. That is not an updraft. That's just a cumulus cloud. An updraft is going to be a big tower, not just one cumulus cloud, but a big tower of those cumulus clouds extending from the bottom of a storm, a flat base, if you can see it, all the way to the top until the cloud stops developing, basically. Your updraft clouds, again, when you get a really big thunderstorm, they're going to look very dramatic. They'll have a very crisp, very cauliflower appearance to them. And the way you see them as a storm spotter matters as well. The more crisp, the more clear, the more high definition that those clouds look like, the more it looks like an actual stalk of cauliflower in the sky, the stronger that storm is on average. So you can see these very dramatic billowing cumulus clouds here, that very distinctive form, but you can see where it's not as distinctive in here, right? So this is where I'm talking about. If all of your cumulus clouds were very fuzzy and not quite as in focus, you still have a storm, it's just not as strong. When it's very crisp, very cauliflower-like, that means that air is rising too rapidly for the wind around it to sculpt it. That's a bad sign, right? That means you've got, or a good sign if that's what you want, that is a very strong storm that you have on your hands. So when we're looking for updraft clouds as storm spotters, there's three things I want you to kind of keep a mental checklist of, right? So what we're looking for to identify the updraft part of a thunderstorm is ideally we're looking for flat clouds down near the base. Now this assumes you can see the whole storm, which as we've talked about in Arkansas is quite challenging due to hills and trees. But I can't teach you how to look at a cloud through a hill or a tree, so I just have to show you these storms in other environments, right? That's the purpose of this. Down low, we're looking for flat, smooth clouds. That's going to mark the base or the bottom of your updraft. Above that, we're looking for these big billowing cumulus clouds extending in a big tower above the flat, smooth clouds down low. If you are below, or if you can see below those flat, smooth clouds, you should be able to see or verify by feel that it's not raining underneath these clouds. So flat and smooth at the base, big tower of cumulus coming from those flat, smooth clouds down low. You can verify that there's no rain underneath. You have found the updraft part of the storm. Now, depending on your perspective, like how close or far away you are from the updraft, it's going to look really, really different. So now I'm going to show you some pictures really close to the updraft, really far away from the updraft, so you get different perspectives. This is close enough to just be characterized as stupid. And you can guarantee if I'm showing you a picture of stupid that this guy was responsible for taking those pictures. So this is so close it is very, very stupid. If a tornado develops here, I don't have enough room to move away. I'm in a lot of trouble, right? But I also know what I'm doing. We were out in this field research team for 5 or 6 years. There's not a tornado threat here, but this is the updraft. Directly underneath the updraft. This is what it looks like. You can't see the cumulus clouds above me. Why? You're under it. So this is where it gets confusing. If you're so close to the storm that you're under it, it looks very different. But look at this cloud doesn't look quite normal, does it? You see how unusually flat and smooth that cloud base is? That's not normal. That's where the air is rising up. That's the base of this thunderstorm. Look where the base transitions into downdraft. Do you see how dramatic and fast that is? So what's this? That's rain. So you can see all the air's moving up, all the air's moving down, and that transition takes place right there. That's me underneath the storm, understanding what's happening. Now, if this had a wall cloud, you can rest assured I would not be sitting there, but this doesn't. So I'm only looking for hail here, And unless you want to find hail on your windshield, I wouldn't suggest repeating this. But that's updraft, up close and personal as you'll ever get. Now, as you look further away, this is more what you'd see in Arkansas. The trees and the hills kind of block the lower part of the updraft. So now you have to look for something else. Well, just because you can't see the updraft base doesn't mean you can't follow the storm's updraft. You've got this big storm here. The updraft, we're going to find the tallest point where the cumulus clouds extend to their absolute highest. Follow that in a path down as far as you can see. And as long as it's cumulus clouds on that whole path, that's another way to visually track the updraft. You don't need radar, right? You just need your God-given eyeballs. That's it, to understand what's happening here. If you knew the updraft is right there, you know where the highest tornado threat is. That's the advantage for visually identifying the updraft. You know where the storm is at its peak danger level. You can either use that to get closer and be a crazy person or to stay away, right, as a storm spotter. I have obviously been part of the crazy person variety, so don't think I'm making fun of you. I've been there. I know that call. From what you really want to do, ideally, if you could just teleport yourself to that magic place to take a good picture of a tornado without dying from the tornado, you would get to the right of the storm motion by about 3 to 5 miles. If you got that perfect position to the right of the storm motion, 3 to 5 miles away, this could be something that you're looking at. Let me explain what you're looking at here. This is the updraft base, this whole thing. Now, whoops, you're zoomed in so close that you can't even see the rest of the storm. But, you know, this is until we are able to invent 3D goggles or, you know, virtual reality goggles, you can't pan your head and see the rest of the storm. This is the whole updraft. Now, inside here, there's stuff going on that I haven't described yet. But suffice to say, this is the part of the storm you probably want to see, right? To know if there's a tornado or not. From the updraft base, you can see this barrel, this kind of dress or barrel shape leading up into the main updraft. All these flat clouds are the path that warm, humid air is taking to move horizontally to get up into the storm. So you're basically seeing where the thunderstorm is sucking up heat and humidity to fuel this massive structure that you see in front of you. Now, from this standpoint, if you're to the right of the storm's motion, that's a good place to be because you don't have to move and the storm will just kind of move from your left to right. You can get this close and be in front of the storm motion and have this thing chasing you, and that's bad. And if you can't tell the difference, don't get this close, ever. You don't have to be a storm spotter. I'm just telling you the ideal position to get yourself to safely do this if you want to. You can stay way, way further away than this and still be an amazing storm spotter. I encourage you to do so. This is a professional storm chaser doing this. It takes lots and lots of training and expertise to get to this perfect location with the perfect equipment at the perfect time. You don't have to do all that. I just want you to stay safe. But this is what you look for. Updraft, 3 to 5 miles away, that's about perfect.
So if you're seeing the updraft on both sides of that tornado, it's either moving towards you or away from you, right?
Right. You probably wouldn't have a picture of that experience because you'd be too worried about your drawers. Yeah. Yeah, that'd be tough. But yeah, from here you're safe because the storm is moving to your right. The only thing that could hit you here is lightning, which is an underestimated threat when you're out spotting. Now, what I want to do with these next few slides is explain this junk under here. So are we good with updrafts? How to visually identify them? Okay. So all this stuff going on underneath the updraft. So what's that all about? Well, again, this is it's similar. It's a storm similar to that last one, but this is different perspective. This is a time lapse, obviously. This is about 20 minutes of time lapse. And so this whole thing is the updraft base. And now this is where the clouds are supposed to stop. There shouldn't be any clouds below here. If there are clouds below there, something else is happening. So what is that something else? That something else is what we often call the wall cloud, right? The wall cloud is going to be your visual cue that, hey, look out, I'm getting super dangerous. I'm thinking about producing a tornado. That's what your wall cloud is doing for you. As a storm spotter, that's giving you the warning. Hey, look out, I'm a tornado threat. Your average supercell, storm that could even produce a tornado, only about 10% of them will ever produce tornadoes. It's not very much. If you see a wall cloud, that number jumps almost to 50%. So that's a big increase in threat, right? You see a wall cloud, that matters. Doesn't mean it's going to happen, but it's a lot more likely than without one. So what is going on? What's causing this wall cloud to appear, to give you that warning? Well, remember I told you that the whole updraft is acting like a giant vacuum cleaner for the heat and humidity all around it, right? Here's the thing, the storm doesn't have a brain, so it's not thinking. It's going to suck up all the air all around it, no matter what. Whether that air is hot or cold, it's going to suck it all up and bring it into the center of that storm. That's all it does. What you're seeing here is when the updraft gets so strong that over here is where it's raining, right? This is the downdraft. When the updraft intensifies, gets so strong, it actually causes the air rushing into the storm becomes so strong that the rain can't hit the ground anymore. The rain gets caught up in that surge to the storm, and the rain goes horizontal, hugs the ground, and gets sucked back up into the updraft.
Is that what makes up the wall cloud then, that rain?
That's the wall cloud. Yes, sir. Very insightful. You got it. So the wall cloud is made up of the rain that didn't get a chance to hit the ground because the winds got so strong, it just moved that air sideways and then tried to bring it back up into the storm. Instead of that rain turning back up, going back up into the sky, it becomes a cloud. And because that air is surging in and just feeding it rain, that cloud gets closer and closer to the ground. So that's giving you the visual warning sign that, hey, I'm becoming very dangerous. I might produce a tornado. Now, whether it does or not, this is where even the modern day science of meteorology fails us. We don't know exactly what balances of ingredients is going to make that a 50-50. Okay, there's a wall cloud. Do we get a tornado or not a tornado? That's where we really need the storm spotters. We don't know. There's no equipment we can use to measure that yet. Yes, sir.
So would you consider, like, with a wall cloud, is there typically broad rotation?
There is. Yep. And that's a really good question because you see this image here. Keep in mind, this is a 15 to 20 minute time lapse. You would never see this motion. At any frame, you would just be looking at this as a still image. And you would have to compare a picture now to when that cloud built closer to the ground to know that it changed. So you wouldn't necessarily see the movement. Now the wall cloud is the smallest thing that you can actually see rotate. Any bigger rotation in the storm itself is impossible. But when the wall cloud really starts to generate rotation, you'll see slow, this greatly exaggerates it, but you'll see very slow movement, rotation in the clouds. And that is a good visual clue that you're leaning more towards the 50% of yes, I'm going to produce a tornado than the no. So that's an excellent question. Here's another time lapse. I just want to show you this perspective that time, the wall cloud is basically already there. I want to show you a time lapse where the wall cloud just appears. So that's this. Again, you can see without diagrams this time, so you can just see the full time lapse. And you can, every once in a while, see a person zip in and out of the frame there at the bottom. It's a time lapse about 4 times normal speed. And again, 15, 20 minutes. It looks like nothing, maybe just some clouds at first. And then you have a very ominous, scary looking cloud there at the end, right? Now, some things to point out about this is your wall cloud. Once that wall cloud is there, the tornado could develop anywhere in it. We don't know any rhyme or reason to which side of it you might get a tornado. Just know that you've zeroed in, right? So this is what we're doing as a storm spotter. We're zeroing in, big storm. Oh, I see the top. I'm funneling down. I'm following the updraft to its base. That's the mentality you've got to have have to visually identify these properly. From here, you'll notice the wall cloud isn't just a block. You see how it points one direction? It's pointing towards the rain because the rain is causing it to be there. Hope that makes sense. So the wall cloud's always going to point towards where the rain is because the rain getting sucked up into the storm is the whole reason you have a wall cloud in the first place. So that's always going to be the orientation. Now, how many of y'all remember the Jonesboro tornado? So now, after everything we've talked about here, I want to show you the non-sped up just series of events that resulted in that Jonesboro tornado. And this is captured from several different videos. This is the RDOT camera. And to set the stage, the RDOT camera, this is the leading edge of a wall cloud. Does that make sense? Your updraft base is this whole thing. Your wall cloud sticks down a little bit below it. And I'll let you see, this is not sped up at all. This is actual real-time coverage. I'll let her run.
What we need right now is everybody to be in their tornado safe spot. This is going across 55, coming right into the heart of town. It's going to be coming right near the mall at Turtle Creek here shortly. It's going to continue.
Is this like, what is that?
See how different it looks from different perspectives? That's somebody directly in the path of the tornado. They don't realize it.
There's a tornado coming out that's going right in town. It's in Jonesboro right now.
Oh, there it is, right there. Zoom in. Can you zoom in on that? Guys, we have a confirmed tornado in Jonesboro. So if you're in the Jonesboro city limits, get into your safe spot. This is real time. This is a tornado on the ground inside Jonesboro.
So again, in the wall cloud, you just, all of a sudden, you see that little thing. And right in here, these people are going to get hit by the tornado, 100%, and they're still videoing. I had to cut the audio because I didn't know how to do the beep thing for all the swear words. As was quite obvious right there. Yeah, what do you say? I can't imagine. But I mean, from that center perspective, you can literally see the debris raining down from the sky, and they still want to video it. So those two guys, they worked at a used car place, and the manager had to drag them in, literally, drag them into the central office, and he saves their lives. Because I swear to God, they're going to sit there and do this as the tornado mows them over, like this is a force field or something, right? It's not. If you've got this in front of your face, the world still happens to you, I promise. Don't figure that out the hard way. So there was a lot going on there in that video, obviously, but I think the biggest thing I want you to walk away from this is, please don't think you can video a tornado until it smacks you in the face. It will kill you. Your phone is not going to protect you from natural disasters. Not just tornadoes, any natural disaster. You are a part of it, right? I know you want the cool video, but you got to stay alive first. So as storm spotters, one advantage you'll have to just watching things on a computer screen is you can feel the world around you. And I want you, as a storm spotter, to take full advantage of that, because feeling the world around you, we're not used to this. We're used to spending our lives in these little devices, but feel it, right? Feel it around you. What are the winds doing? What's the grass doing? It all tells a story. You just have to know where to look for it, right? To make sense out of it. So in this case, obviously we've got a big tornado here, but I want you for once to ignore the tornado. Know that it's there, and that tornado is a giant low pressure system, which means everything gets sucked in towards it from all directions. The winds that the regional airport here don't matter when you're that close to a storm. They're being dominated by the storm. So the winds are always going, when you're within 5 miles, the winds are going to point in and towards the tornado, in and towards the updraft, within 5 miles. So if you're struggling, if you're seeing low-hanging clouds and you're not sure what you're looking at, this not being the best example, because there's obviously a tornado there, close your eyes and feel the world around you. What's it telling you, right? So you're taking this picture, you feel the winds. How are the winds hitting you? At your back, right? So if you're spotting, if you're looking at the updraft, on average, if you're really looking at updraft, the winds will be hitting you at the back towards the thing you're looking at. If it's downdraft, the winds will on average hit you in the face as you're looking at the thing you're interested in. So that's something that there's nothing I can do in training to help you out with this, right? You just have to feel it. Understand that the storm is talking to you, and it's up to you to get the whole story by feeling what's going on around you. You do that, and Mother Nature will guide you in the right direction. You got to be willing to do that. Slow down your mind, right? This can be really exciting. Slow down, make sure you're seeing what you're seeing, then keep yourself safe, then report it. Wanted you to see some drone footage of a tornado taken by some researchers, just to give you an idea of how non-solid these things are, and they look very, very different if you're up close and personal. And you really get a feel for it here. You see how far away the debris sits in the air? How far away from that center of circulation? Well, you don't need to be in this. This will kill you. You can't be close to a tornado. It's not this solid object that you're, oh, I'm in, oh, no, I'm out. You don't get to play that game with a tornado. The winds increase as you get closer to the center, like a hurricane, just on a very tiny scale. Don't get too close because you could accidentally be in the tornado and not even realize it. So don't be that person, please. These people use drones. So unless you're a drone, don't get that close to a tornado. So this is a different perspective. I have a lot of photography friends, and so instead of doing a time lapse, this is what happens if you just leave the shutter open at night. It's an exposure, right? That's what the film technique or camera technique is called, an exposure. You leave the shutter open at night for a really long time to collect all the light. So this is like a 2-minute exposure. You stack the images and you can see, even though it's at night, you can see everything going on in this storm. Just please don't let this color you into storm chasing or storm spotting at night, because you would not see this. You would see flashes and then would be totally blind. You can only do this with camera equipment. But you get a nice 3D perspective. Your tornado is the lowest part of your updraft. So to find a tornado, you have to find updraft first. Tornado is the lowest part. Then you've got the flat, smooth clouds down low, kind of the wall cloud mixed in with that, and then the big tower of cumulus all the way to the top of your storm. That's your updraft, right? And you can see it's tilted. It's not straight up and down. The whole rest of the storm is downdraft. So to give you that perspective, when we issue a tornado warning, it's for the whole storm. Look at how itty-bitty that tornado is compared to the whole storm. The point, the whole thing is, when we issue a tornado warning, it's not that you're guaranteed to be hit by a tornado, but we can't track this thing specifically on radar, so it's close enough to where you might as well shelter so you just don't die on accident, right? That's the whole point of a tornado warning. We hope and pray you don't actually get hit by a tornado, but it's close enough that you might, so take the protective action. That's all we're saying with those warnings. I don't want you scared. I want you to understand the threat realistically. You probably won't get hit by a tornado, but you still need to take cover anyways. That's really important. Any questions about updraft before I transition to downdraft? Okay. Downdraft clouds. So when we look at downdraft clouds, on average, They are way, way scarier than your updraft clouds. Without a wall cloud, your updraft clouds are super, super boring. I mean, who stares at a flat ceiling all day, right? There's no fun there, but that's how updraft clouds start. It's just flat clouds, nothing fun to look at. Your downdraft clouds, that is never the case. Strong storm with a strong downdraft, it's gonna look nasty. If it looks like the alien mothership has landed and it's invading your neighborhood, it's probably the downdraft part of the storm that's doing that thing, right? It's not that a tornado is headed your way, but some bad stuff is. So let's talk about what that bad stuff looks like and what those impacts could be. So downdraft clouds are low-hanging, scary-looking clouds. It looks nasty, it looks scary, and behind it, it's very, very dark, very ominous. Now, with all that in mind, why is it so dark and ominous? Why does it look like some scary movie background? Rain, right? That's it. It's rain. It's only scary because of rain, which is a part of the downdraft, which is all air moving down, which means this has nothing to do with a tornado. Yeah.
Just a perspective, it takes a lot of rain to block out the sun, but the sun's on the other side. If you can't see the sun, you got that much water between you and the sun.
That's a great perspective. And yeah, if there's enough rain to block out the sun, it's heavy rain, right? It's doing some bad things. It's just not in the form of a tornado. But you know, behind this leading edge of cloud, when those clouds come by you, this is when the winds shift suddenly. This is when the temperature drops. Further behind that, you get into the very, very heavy rain. And like he mentioned, the rain is heavy enough to where you can't see the end of the hood of your car. This is no nonsense stuff here. This isn't just rain. It is a deluge blocking your entire vision. So you don't have to be scared of this. You just have to be prepared for what's behind that line. If it's coming at you, you can't drive through this. So you see this and there's no other option. You pull off the road, right? Find a rest stop, something. There's no skill. There's no driving through this. It's going to blot the sky if you drive through it. But there's not a tornado. These are all signs of downdraft headed down and away from the thunderstorm and approaching you. When you get a really nice, good open space, and this is from Arkansas, good open space, panoramic view, you can see what the leading edge of these straight line wind storms usually look like. And it's going to have this very distinct appearance, low hanging, ragged looking clouds organized approximately in a bow on the leading edge of that storm. That's the wind being pushed out and away from that thunderstorm. The thunderstorm's trying to get rid of all its rain, right? All that hot air and wind and moisture that the storm sucked up. This is how the storm gets rid of it. It's trying to get it out of place. If you're in the way of that, you're going to get hit by the stuff that the thunderstorm is putting down on the ground. That's largely going to be very strong straight line winds, very heavy rain, and then maybe some hail at the backside of the storm as well. The reason why the storm has this very traditional bow shape is that the winds on the leading edge of the storm, they're not all the same strength. At the middle of that bow is where the winds have pushed out stronger than anywhere else. So think of it like a NASCAR race, right? That part of the storm is just moving faster, and everything else is a little bit slower behind it. That's why you have that bow shape. So your peak winds are going to be at the peak of that bow on average. And if this is headed towards you, you do not want to be on your boat. Unless you're on some sort of like U.S. Navy ship, your boat is not going to be okay through this. So don't do it, right? Get the boat to a dock and get off the water. If you see this approaching your vehicle, just know you're going to be hit by very strong winds, very heavy rain. It's going to be quite difficult to drive. None of this, though, indicates a tornado. And I want to show you specifically where spotters get into trouble. If you don't look at the big picture first, that's where things get confusing. Now, big picture here, big long line of clouds, low hanging, very dark behind it. Do you find it pretty easy to tell that this is downdraft and not updraft? Okay, what if you're of the single-minded focus that you're looking for tornadoes? What is this thing? Scud. Some of you know the actual name of it. That's good. But yeah, this little cloud here that kind of looks like a low-hanging ragged cloud has a similar shape and appearance to a wall cloud is not. These little weird low-hanging clouds, they're there because this is a big bag of wind going from the top of the storm down to the ground. When that wind hits the ground, it doesn't just stop, it bounces. And that bounce is what we call turbulence. So the leading edge of the downdraft is extremely turbulent, which means it creates these weird low-hanging clouds. They spin, they rotate, they're there 1 minute, gone the next. That's all downdraft clouds. This is no sign of a wall cloud or an updraft of any way, shape, or form. You need to look at the big picture first, because that means if you understand the big picture, none of these little clouds matter anymore. Big picture brain says this is downdraft, don't have to worry about updraft, let's move on to something else. Does that make sense? All right. Downdraft clues. The 3 things I want you to keep in your brain as a checklist, right? Ragged and choppy clouds along their base, usually organized in a big line out ahead of the storm if you happen to be watching on radar, and usually very dark, very streaky appearance underneath those clouds. It is not sunshine, it is very, very obvious something is reaching the ground behind these clouds. That's downdraft, no matter how it appears. And this one's pretty weird, right? You've got these clouds at a much lower level than they are here, but this whole thing is just downdraft. Big picture. And there's no way somebody took this picture while they were driving. That would just be stupid. So we're going to move on to the next picture here. So remember what I told you about feeling the environment as a storm spotter, right? You feel the environment. Well, look at how the wind is interacting with this young lady's dress. She's looking at the clouds, right? Would you say the wind is hitting her in the face or at the back? It's obviously hitting her in the face. So that means wind's in your face, the storm is blowing stuff away from it. That means you're looking at downdraft. You don't have to know anything else, right? If you can't make sense out of whatever's going on here visually, close your eyes, feel the environment. What is the full picture? What's the whole story telling me here, right? You can figure it out as long as you know what to look for. This young lady's telling that story for you. Wind's in the face, more likely looking at downdraft than updraft. Make sense? All right. This is a video from inside the downdraft, and just like the previous videos, I don't know how to beep something for swear words, so when the audio just drops, that's what I did. So enjoy. They weren't too happy about that.
This is easy 100-mile-an-hour winds.
It's not 100-mile-an-hour winds.
Oh, our tree's gone! We lost 2 trees! Our front yard is gone. Oh, damn, I love those trees.
Right, so this is very typical damage that you get from being in the downdraft. Do you think that would have hurt if you were hanging out by those trees out there? Yeah, right? That's not cool. There's no tornado there. Straight line winds are dangerous. That was not 100-mile-an-hour winds, I promise you that. But that was a good 60, 70-mile-an-hour winds that you're looking at right there, right? Feels like 100 because you've never seen it before. You don't watch the trees in your front yard topple very often. But those root balls, yeah, we're talking 60, 70-mile-an-hour winds, probably with some wet soils knocking those trees down. Straight line winds can still do a lot of damage. I don't want you to only be concerned about a storm when it has a tornado. Straight line winds hit more people and are a threat to more Arkansans than tornadoes. So here's putting this all together. Now this is assuming that you have, I'm going to steal your handout here. I didn't explain much on this handout about the bottom left-hand diagram, and that's for more advanced training for people that are going to be in their vehicles no matter what I tell them. That's for folks that plan on being crazy people and driving around the storm to look at it. I'm showing you pictures of people that made it to the right flank and are perfectly positioned to view the interesting part of a supercell without dying. I can't stress this enough. Getting here is very, very difficult. Years of training and experience. I don't want you to just drive out there and try to do this. But if you get here, I do want you to make sense of it. Because you know what Mother Nature won't do is Mother Nature is not going to zoom in on the updraft and ask you to diagram it. She's not going to zoom in on the downdraft and say, hey, what's this, guys? She's going to put it all together, and you've got to make sense out of everything the storm is telling you. Now, in this specific case, this only works with a supercell, and that you are positioned exactly to the right of the storm motion. If you get there, you're going to see this, and your ability to make sense out of what you're seeing goes a long way in you staying safe and not dying if you plan on being in your car. If you can get here, I've told you about the updraft, right? I've got it labeled for you. This has to be updraft, and the heavy rainfall. We know that's downdraft. So I've made it pretty simple. A storm is composed of updraft, downdraft. The more the updraft and the downdraft are separate, the longer that storm lives, the more dangerous it becomes. What that doesn't explain is the left-hand side of this screen. What the heck, right? There's more than what I've described to you. There's a whole part of this storm here that shouldn't be there. This should be the end of the storm, right? This is the back side. This is the updraft. Everything should go that way. So why not? Well, this storm is rotating. Because it's rotating, it's a supercell. So this whole storm, I'm the updraft right now, the whole storm is rotating. And the rain that's over here, because I'm rotating, I'm going to bring some of the rain back behind me. That leaves you in a situation where you've got me, the updraft, in the middle. Most of the rain is falling here, but because the updraft is rotating, I'm dragging some of the rain and placing it where it doesn't belong, on the backside of the storm. Not supposed to be there. That's what we call the rear flank downdraft. And now here's where I want you to put the three steps we talked about, the three characteristics of updraft and downdraft into practice, right? We look at these clouds here. Is this totally flat and smooth? It's wavy, right? Now you can't see if there's anything falling here because it's overexposed, but there is some very light gray streaks going from the top of the picture down to the bottom. It's very hard to see in this picture. So low-hanging, ragged-looking clouds with streaks behind it. What type of clouds does that have to be? Downdraft, right? So I've got downdraft here, I've got downdraft here, updraft in the middle. Well, this is what the science of meteorology tells us about this unique situation. I've got an updraft that's rotating between two areas of downdraft. One of the areas of downdraft, the updraft itself is dragging behind it, along with it, right? As these two areas of downdraft get closer together, what happens to me? I get squished. And that's, as the science of meteorology, we understand it, that squish is what makes a tornado produce. So that squish, the downdrafts coming together, if that happens at the exact perfect rate, then this circulation here will get squeezed, causing that circulation to do what? Yeah, it'll push up and push down. Have you ever watched the Winter Olympics before? You go to see an ice skater do her triple loopy thing. What does she do with her arms? Brings them in, right? It's not art, it's physics. She's using physics to generate spin for her routine. Well, the atmosphere does this without thinking, right? You've got a vertical rotation. It's being squeezed between two areas. It has nothing else to do but to generate spin, which builds up and down. When it contacts the ground, we call that a tornado. Here's the catch. If that rear flank downdraft is too fast, the storm just dies. It wipes all the hot air out of the way, storm dissipates. If that rear flank downdraft doesn't push enough, there's no squeeze. The wall cloud just sits there, it never produces a tornado. What is that right rate of squeeze? We don't know yet. We don't have sensors that can survive that atmospheric interaction for that exact point of a tornado developing. So that's where you come in. You understand all this is happening. You see a wall cloud, report it. That wall cloud starts to rotate, report it. You see a funnel, report it. This is progressing, right? You're not talking about one thing that stays in that state forever. When you report the progress of this, that means something to us behind the radar. If we haven't yet pulled the trigger on a warning, that could be the thing that tells us, hey, I may not see it on radar, but everything they're saying makes sense. Here's the order of events, I'm gonna go ahead and do it. That's how we help each other, right? But that only happens with understanding. Oops, I did want to point this out again. So on that radar image at the very beginning, you were able to pick out the hook echo pretty easily, right? On that like seventh thing I showed you. This is what a hook echo looks like in real life. It's very different. Remember, the radar sees an X-ray, kind of a negative of what we're seeing on this screen. The radar sees none of the clouds, but it sees the light rain back here. It sees the heavy rain here. And you know what it sees here? Nothing, because nothing's falling from that part of the storm, right? You start to see the problem why radar can't see tornadoes efficiently is because they develop from the updraft. There's nothing falling in the updraft for the radar to see. So until there's a tornado producing damage, radar doesn't see it. That's why we need humans. Yes?
So when you're watching the weather guy on TV or whatever, and he shows on the radar where it's indicating hail, is that because the radar is seeing solids moving up? Or can it see that?
Yeah, it can. It's basically seeing all the intense returns aloft in the storm. Because radar's not just looking at one level. Yeah, once it does a full loop, it tilts up a little bit, then does another scan, tilts up again, and keeps doing that until we get a full 3D picture of the storm.
Okay.
So when those big returns come in from aloft, that's where those hail markers are going to come from. The stuff that's lofted up by the storm that hasn't hit the ground yet. And it may not still be hail when it hits the ground, right? The radar could be up there 30,000 feet. Well, it doesn't mean it won't mostly melt before it hits the ground. So, but the radar will tell us when there's ice aloft, yes. So the other thing that you can figure out if you're a storm spotter making sense of these clouds, if you've got the updraft right here, right? No rain, updraft base, something interesting going on in there. Not sure what exactly, but if you can pick out the updraft and the main downdraft, because now we've got two, right? So this is the key as a storm spotter to keep yourself safe. If you're going to pick out, the updraft is somewhat easy in the middle of the screen here, but how do you differentiate the main downdraft from the rear flank downdraft, just visually? Rain intensity. What does the rain, how can you tell where the intensity of the rain is the highest? Darkest, right? So the darkest side is going to be your main downdraft. You don't need a radar. Find the updraft, find the main downdraft. The storm is always going to move from its updraft towards its main downdraft. So if you don't have cell signal, if you don't have radar coverage, if you don't have a buddy telling you which way to go, know that this thing is moving from where it is right now towards where it's raining the heaviest. That can help keep you safe. If this thing just keeps getting bigger and bigger, what's actually happening? It's moving towards you. This thing does not have turn signals, right? This coming right at you, it's not going to make a sound. It's totally silent. This wall cloud, once it's there, it doesn't really change size at all. So if it keeps getting bigger and bigger, it is not getting bigger and bigger. It's getting closer to you. That's the only warning sign you have to get the heck out of there. And if you need to get the heck out of there, you need to know which way to get the heck out of there. So if we know that this is where the tornado's moving, which way do I drive to get the heck out of there? The opposite, right? So the main reason to understand this is not so that you can tell us which way the tornado's moving. It's so you know where to escape. That's why you need to know this, to save your life if you're going to be out there doing that. Otherwise, you just report what you see. And in this case, we've got a wall cloud, and I don't know if that's reaching the ground or not. So we would just call it a funnel. How do you find out if it's a funnel or a tornado? Debris. You would have to visually see debris to know for sure it's a tornado. From this distance, you cannot do that. Do you drive closer? No. No. Ever, never, ever, ever drive closer. Report what you see. You're safe here, right? Don't put yourself in a position where you're not. No report is ever worth your life. I can't stress that enough. No report, no circumstance is worth your life to get closer to this to find out what's really going on. I don't care. Don't do it. If you report a funnel and we can't make sense out of that to make a good decision, that's on us. It's not on you. Your responsibility stopped with, hey, weather service, wall cloud, I see a funnel, I can't tell if it's on the ground. That's it. You're done, right? You've done everything you need to and more by doing that, so don't go further. How do you know if it's a supercell? A supercell is just going to change the appearance of the updraft. So when a storm is a supercell, the winds around it are going to sculpt the updraft into a very specific shape. One that is, you can kind of see here, you see how these clouds are, oops, of course the laser's not going to work. These horizontal lines that make the clouds look like one layer of clouds stacked on another. So that appearance from the side, that stacked plate appearance, or kind of like the stack of pancakes on the side, that tells you that the whole storm is rotating because the winds have been sculpted around it in a circle to make these very distinct horizontal plates. So if you look for the updraft, and instead of seeing those nice big tower of cumulus clouds like I talked about, if you see these horizontal plates, you'll know that the whole storm is rotating and that it's a supercell. You don't need to get into it to find out what's going on. If it's a supercell, it's got golf ball size hail and 60-mile-an-hour winds. It's not your job to sample that for us. It's going to do bad stuff to somebody. Report that you've got a supercell. Again, your job is done. We thank you so much for everything you've told us. I really like this picture here because I think it shows you that process of the storm taking on rotation, but at the same time, you can still see where the updraft is dominated by those cumulus clouds, right? So we still have this big tower of updraft indicated here, but you can actually see the big tower of cumulus clouds being spun into these horizontal lines that we call striations. That's all you need to know, that this thing is a supercell and capable of doing a whole lot of damage. You don't need to find out what that damage is, so don't do it. I like this time lapse. This was maybe an hour-and-a-half time lapse for a storm in northeastern Kansas that was moving at 1 mile an hour. So 1 mile an hour for over 60 minutes, and you see what's happening, right? The whole storm is rotating. The updraft is maintained exactly where it is, but you can see the storm dragging downdraft behind it and the RFD smeared in here, and then most of the rainfall occurring out here. It stayed in that steady state so that you can just see what that whole storm is doing. Again, this is not visible. This is a 1 hour time lapse. The motion is so subtle you can't just watch it, but that's what's creating the shapes in those clouds. If you do see something, yeah, I did take out the phone number there and hadn't put in the email address, but this is all in your handout here. The email address is nws.littlerock@noaa.gov. It'll be on the central left-hand side of your handout there. The only thing I am going to point out here, you can use that email address. You can also download an app called MPing, M-P-I-N-G. It's a free app that's going to allow you to use your phone to tell us, it'll use your phone's GPS to allow you to tell us whether it's raining, hailing, wind damage, tornado, flood, whatever's happening in your neighborhood. You can submit that anonymous report. This app was developed as a collaboration between National Weather Service, NASA, and the University of Oklahoma through their Severe Storms Laboratory and Research Center. So this is as good as it's going to get as a direct line to us. It's just anonymous. The more good people that put in reports, it makes the bad reports stand out. So yes, you can submit bad reports on here and you're not going to the bad guy jail for the rest of your life, but we rely on good citizens doing the nice thing and submitting good reports to us to help identify the ones that, that obviously stand out from the noise. These are the things we want you to report to us. Any of the bad things that a thunderstorm can do. Damaging wind, you don't have to measure the wind. Please report the impacts, trees down, roof damage, so on and so forth. Whatever it is, report it to us. Obviously, if you see a tornado, we need to know about that pretty quick, right? So please report that. Heavy rain and flooding and hail. Of these four things, what do you think kills the most people year in and year out in Arkansas? Flooding. Yeah, by far, flooding. This gets the most media attention, and I get it. They're interesting. There's lots of action movies about them, but tornadoes, they don't do nearly as much damage as the heavy rain and flooding. The heavy rain and flooding is the biggest thing. It's just hard to get attention on it because it's not something that's dramatic to show on television or film in any way, shape, or form. Is it a tornado? We've already talked about this, so I'm not going to sit there and harp on it, but the way to tell if something is a tornado is to use that top-down approach. Am I looking at updraft? Do I see a wall cloud? Do I see a funnel? To know it's a tornado, you have to visibly see debris. I don't care if the cloud touches the ground. Clouds touching the ground don't hurt people. What do we usually call a cloud that touches the ground? Fog, right? You ever step outside on a foggy day and get wind damage? No, right? It's just fog. So a cloud touching the ground doesn't matter. We need to see the debris. So is this a tornado? Yeah, right? The cloud doesn't touch the ground, but the cloud is irrelevant. The cloud doesn't make up the tornado. The tornado is wind contact with the ground and the storm at the same time. You have visual evidence of that here because of the dust swirl. Here, this was reported to us in Conway, 6 or 7 times as a tornado that wasn't a tornado at all. It was just a thunderstorm collapsing, sending dangerous looking clouds into the city from the east. This thing is a part of a shelf cloud, looking at it from the side. This was reported to our office so many times as we didn't issue a tornado warning because there's literally nothing on radar. And it's Conway, it's right by our office, right? So we knew something was off, but this is what it looked like. You can see the tornado shape in the clouds, but you're failing so many things along the way. Number one, where's the updraft? There's none. So why are you thinking tornado, right? And that's the difference between a storm spotter and some random person just looking at clouds. Big picture first. What's the big picture? Not updraft here. So don't worry about tornado if the first question cannot be answered as updraft. 20-mile-an-hour winds were noted out of Conway's airport as this moved by, right? Sound the sirens. Not so much. So please let us know, right? Answer the questions in your head. Follow those mental checklists, top down. Dust devils, they look like tornadoes, and they kind of are, just on an itty-bitty scale. It'd be really nice if you could stop a tornado like that, huh? Stomp on you, go away. If you are in the path of a tornado, what do? Where do you go? So this young man, I like this example because this young man, he knew where to go and what to do when it mattered, even though he was home alone. What would you say happened to his house? It's destroyed, isn't it? So the tornado completely destroyed his house, yet he survived unhurt exactly where he is because he knew exactly where to go and what to do when it mattered. And this is the result I want for you and your family. I cannot stop a tornado from destroying your house. I'm just sorry, I can't. And we may not ever have the technology to do so. But I can help get you information to know that you want to go to the center part of your house, right? If a tornado is approaching. Your goal here, general rule of thumb, put as many walls as possible between you and that tornado. Find the part of your house where that is true. that's going to be your most likely tornado shelter. Lowest floor, most central room. If you can find a room that also has metal pipes in the wall, that helps, right? It's extra support to displace debris. But get to that lowest floor, central room, and if you can, duck down, protect your head, your face, the central part of your body. Take debris strikes on your back and rump, right? I mean, literally, I know it's funny, but you're much more, you can handle strikes there where you can't handle them in the front of your body. Your whole goal is to not get hit by debris. That's what generally kills people. If you can avoid being hit by debris, you can survive a tornado. You really can, no matter what the circumstance, if you can avoid getting hit by debris. So make that your goal. Any questions about where to shelter in a tornado before I move on to microbursts? Okay, so microbursts, they look like tornadoes, but it's just a thunderstorm collapsing. So a microburst happens when all the heat, all the rain that gets supported up by the updraft, when that storm starts producing rain, that cold air rushes out, it knocks all the hot, humid air, keeping that storm upright out of the way, and the whole thing collapses. The ironic thing is, if you're right under it, you just get super wet. You don't generally get damage. Where you get the damage is when this stuff hits the ground and then spreads out. So when that big ball of water hits the ground, it has no choice but to spread out in all directions. And as it spreads out, that's where damage is produced. So you don't get damage right under the microburst, but right next to it. And these can often happen without warning because the storms go up and they fall back down within 30 minutes. There's not enough time to see any winds on radar before the damage is being produced. These are very common in the summertime. They don't last long. If you get damage, it'll be gone. The whole thing's gone in 30 seconds. But that's a big shocking thing when you don't get rain and all of a sudden wind rips through and knocks the trees down, right? This is what it can look like in a school setting. Microburst, no thunderstorm warning for this. It's HVAC, some kind of one of the big HVAC things for the building. But I hope this shows you a couple of things. For one thing, a microburst can happen very, very short time periods and produce quite a bit of damage. But look how fast it's over. You see how bright it is outside all of a sudden? Not even raining there. The winds rip through and then they're done. Their thing is done. The second thing I want you to learn from this is if you're responsible for sheltering humans from a storm, you never stick kids or adults or anybody in big open spaces with very tall walls and no horizontal bracing. You stick a bunch of kids in a gym in the middle of a storm, you're fixing to get them all hurt real, real bad. Don't do that. This is why we find hallways to put kids in. You want hallways or basically any space with short walls or shorter walls and a lot of horizontal bracing in between. So you want that horizontal bracing to keep the walls off of you, basically. A gymnasium is just a big kite for the straight line winds. They always collapse. They're always the first things damaged. You can fit a lot of people in there, but that's just going to get a lot of people hurt. Find better shelters. Lightning. You're not going to get much of a heads up on this, right? If you're outside, not in your vehicle, you can get struck by lightning. And that could really, if it doesn't kill you, it's going to ruin the rest of your life. So avoid it. That's a big risk for a storm spotter. Don't stand outside if you don't have to. Don't underestimate lightning. Some of the common misconceptions. It can only lightning if it's raining on me. No, lightning can strike 10 miles away from where it's raining. Lightning's always going to hit the tallest object. You see the opposite happening on this beach. The lightning actually hits the lowest object around, right? Lightning isn't going to behave to these, rules of thumb that you've heard your whole life. If you're outside near a storm, lightning is a threat. Arkansas Athletic Association has the best rules of thumb. 30 minutes until you hear the first, after you hear the first rumble of thunder or see the first flash of lightning, go inside and wait 30 minutes before you resume outdoor activities. That's it. That's simple. That'll keep you safe from lightning. You can just be in your car to stay safe from lightning. Your car gets hit by lightning, your car's not going to be okay, but you will as long as you're not touching the outside of the vehicle. That energy will tend to transfer along the shell and then empty into the ground and not hit you. This is the power of lightning. And not to put too fine a point on the matter, but if one lightning strike can do that to a power pole, don't think too hard about what it can do to a human. Just know that you don't want to be that person, right? Don't get struck by lightning. Just the basic safety precaution, be in your car, windows rolled up, that'll keep you safe. Driving in storms is dangerous. You don't have to be the semi-truck. If you're just next to it, imagine what could have happened. So, I mean, clearly the semi-truck driver did amazing, right? But what if you're the car driving next to him? You don't get the heads up that he's going to turn into that turd, right? I mean, things get bad real quick. Don't drive in severe storms. I realize I may not be the best person to tell you this. This is a picture not from Oklahoma. This is Northwest Arkansas, 2022 or 2024, I forget. At any rate, this hail was so large, 5-inch hail, it didn't just damage the shingles, it went through the shingles, through the decking of the roof, through the insulation, into the living room. Large hail can be deadly. It rarely ever is. Do you know why?
Stay inside.
The small hail already hurts, so it convinces people to run inside before it gets that big.
Insurance for the
Yeah, exactly. Oh, that had to be, you did that on purpose, right? You made the hail fall on your roof. So flooding. I'm not going to have very much time to cover this, especially for the purposes of a video, but just know that flooding is by far the #1 way to get yourself killed storm spotting. 100%. If you're so focused on keeping up with the storm that you just decide, oh, my vehicle can handle this. I've driven this truck for 40 years. I'm good. And you drive into the water. That was the last decision you've ever made in your life. Don't be that person. You never know what's under the surface of the water. You really don't. I don't care if you've driven that road every day for the last 30 years of your life. If the water is on top of it, you don't know if the road is still there. Don't be the guy that finds out the wrong way. When his vehicle went into the water, the whole vehicle didn't just sink straight down. Why did it go down front first? Heavier, right? The engine's the heaviest part of that vehicle. What else is in the front of the vehicle that kind of matters? The human. Right? Unless you were born on Krypton, once the cab of your vehicle is underwater, there's no getting out. You're stuck until it fills up. Unless you're a Navy SEAL and prepared to hold your breath for 2 minutes, that ain't going to end well for you. So do the thing and not get yourself into this position in the first place. Turn around, don't drown, right? We try to preach this to schools everywhere, but I really want you to take it to heart. Don't put yourself in a situation where you're going to die just to get a report or to chase excitement. We'll see if I learned you anything. This is your part to show me whether I did a good job or not. What do you guys think of these clouds? What can you tell me about them? Updraft. Hey, very good. Strong updraft clouds. So updraft clouds, one of the mental things we're looking for, big tower of cumulus clouds, right? Very crisp, very high definition in a vertical line. Yes, updraft, strong updraft. What about this? Downdraft, right? This is a shelf cloud. That's kind of what that's the terminology we use for the leading edge of those really long downdraft clouds. But yes, you're absolutely right. You got the key point. Downdraft. That is what that is screaming. Low-hanging ragged clouds, very dark behind it. This is like 1980s pixelated, and I apologize for that, but what is this? Yes, I needed to zoom in very tight to only get the wall cloud, but that is what I wanted you to report. So awesome. You guys are either making me look good for the video, or maybe I taught you something. How do you know for sure that this is a tornado? You've got debris, right? And if you can't see this, what do you report to us? Is that okay? Yeah, that's enough, man, right? It's not your job to confirm a tornado. Let us know you got the funnel, that's enough. Your safety always comes first. What about this bad guy? This is like the advanced question. Supercell. Awesome. Strong updraft, supercell. Now here's the bonus question. Which way is this thing moving? How do you know it's moving to the left?
Downdraft, heavy rains.
That's where the main downdraft is. You guys are absolutely amazing. Thank you so much. There is information on how to get your certificate on the handout there. With this certificate, if you print it out as is, your name here will get credit for all of the wonderful training you had today. I highly encourage you to actually type your name in there so you get personalized credit for taking this class. And that's all you'd ever need from us to show that you're a trained Skywarn spotter. There's our contact information, and thank you all for coming out tonight. Really appreciate it.